All right, so let's take a look at how to use the Ka and Kb formulas. So just taking a look, getting my pen ready here, at talking about when to use them. So when you're looking at acids and bases, if they're not in equilibrium, we're not going to have equilibrium constants. So we want to be able to identify strong acids and strong bases. So for strong acids, just remember that it's above the gray line in the data booklet. And for strong bases, you want to be able to see that you have hydroxide in your formula. So like NaOH would be a strong base because you have hydroxide, or barium hydroxide. Anything that has hydroxide will be a strong base. If you have a strong acid or a strong base, they're not in equilibrium because you get 100% products. So you just use the formulas you would have learned in previous chemistry courses. So plugging it straight in and then solving. Now, if you have a weak acid or a weak base, they want to react with water and they produce hardly any product, less than 1% usually. These products then can come together and produce reactants. So they are in equilibrium. And because they are in equilibrium, we can't just go and use the previous formulas. We're going to have to use some new formulas, the Ka and Kb formula, to solve. And then once we find what we need, then we can solve for pH, pOH, and the concentrations of hydronium and hydroxide. So here's our first example, a simpler one, finding the Ka value of an unknown weak acid. So if it is a weak acid, we know it's in equilibrium, so it will have a Ka value. And the formula is concentration of hydronium divided by the concentration of the weak acid minus the concentration of hydronium. When we're plugging this in, one of the things we talk about, because it's less than 1% of the products, there's hardly any hydronium. So if you have it, use it. If you don't have it, you can ignore the value in the denominator. So when we're plugging this into our calculator, we're just going to replace, and I did miss that this is squared, so make sure you have a squared there. So to get from concentration from pH, you go 10 to the negative pH. So I'll have 10 to the negative 3.42, and this will all be squared, divided by the concentration of the weak acid minus concentration of hydronium, which is 10 to the negative 3.42. So I rather work with exponents, but you could plug that into your calculator, get the number, and carry on from there. So we will plug that all in. We'll want to keep 2 significant digits because this one has 3 sig digs. When you're taking a look at the pH, it's only the digits to the right of the decimal that are significant. So that has a significance of 2. And we will see our answer is 5.9 times 10 to the negative 6. And your equilibrium constants have no units, so that would be your final answer. Now taking a look for Kb, in this one, a little bit more work. What is the pH of a 0.020 mole per liter of sodium acetate solution? So we want to recognize this when we break it apart into Na positive and acetate, which would be CH3COO negative, that this part here is a weak base. And we could tell that as well because it would be listed in the conjugate base column in your data booklet. Now, when we are going to set this one up, if it is a weak base, then we're dealing with Kb and not Ka. And the Kb formula is the OH ion squared divided by the concentration of the weak base minus concentration of OH. Now, when we're going to do this, we don't have the Kb value and we only have the concentration of the weak base. So the other part that we can do is look up the conjugate acid to our base and get that Ka value. And the Ka value of that is 1.8 times 10 to the negative 5. So that is in our data booklet. And I'm just looking at the conjugate acids, Ka. Then there's that connection between Ka and Kb, and that is through the equilibrium constant of water. Kw divided by Ka will equal Kb. So we can now go 1.0 times 10 to the negative 14, which is Kw, divided by 1.8 times 10 to the negative 5, and we would get 5.6 times 10 to the negative 10. So this is our Kb value that we can use in this formula over here. And then we'll be able to ignore the OH in the bottom because we want to solve for OH. And let's start doing the work for that. So we have 5.6 times 10 to the negative 10 equals the concentration of hydroxide squared divided by the concentration of the weak base. So again, I'm ignoring this value in the denominator because it is very, very small. So if we want to find hydroxide, you can ignore it in the denominator. If you have it, we use it. So now we just want to isolate the OH concentration. So multiply both sides by 0.02. And once you do that, then once you've multiplied, then your last step is to square root to get OH alone. So when we multiply there, we're going to get the OH concentration, sorry, this is getting nice and messy, to be 3.3 times 10 to the negative 6 moles per liter. I would have a longer value here, so don't round too early. Keep the whole value in your calculator. And then from there, if you have concentration of the OH ion, then you can find POH by taking the negative log of the hydroxide concentration. So we'll take that value that's in your calculator and plug it in, take the negative log of 3.3 times 10 to the negative 6, and you want 2 significant digits, that's 2 points after the decimal, that we'll write down. And then your very last step, and that's to get POH, is to go 14 minus the POH to get pH, because that's ultimately what the question's asking for. But we can't deal with pH until we've done all this work with the bases. And your final answer here should be 8.52. Okay. So that's having or using our equilibrium constants for acids and bases, using those two to three formulas. I hope this was helpful. If it was, please give me a like and a follow. And I would love if you could subscribe. If you have any videos you would like me to do, please just let me know in the comments. Thank you.